All right, now we're going to look at some other applications. Again, it's kind of a plethora of examples that could get used for related rates. So we'll just look at two, and then we'll see a bunch more when we do practice problems in class. All right, so this one goes back to an example we did in our previous related rates videos. All right, we have these two ships moving, but the thing that we're looking for is going to be a little bit different. All right, again, so let me pause real quick, draw the picture, and then explain what we're looking for. All right, so here's the picture we have. We have our boats traveling in different directions, and the only real difference between this and the previous related rates videos, instead of looking at the distance between the boats, we're trying to figure out some information about this angle between the boats. All right, so we're trying to find some information about this angle. All right, so what can we do? All right, we always have to start off with some equation that relates the things that we know and the thing that we're looking for. So we're looking for an angle, and we know some distances related to this picture. All right, well, it's a right triangle. We talked about that before. There's a right angle there. So if we're looking at a right triangle and an angle, we can use SOHCAHTOA. And in this case, we know the opposite side from theta, and we know the adjacent side, so that's going to be tangent. So tangent of this angle, theta, is equal to, we called this lowercase b, and we called this lowercase a before, so it's called them the same thing, and that's going to be b over a. So tangent is TOA, opposite over adjacent, right, b over a. All right, all of these quantities are changing, because as the ships move, you can imagine the angle is going to change. It's very rare that it would just kind of stay the exact same because things are moving around. And we definitely know the distances are changing, b and a, because these ships are moving. So we can't plug anything right away, so now we have to take derivatives. All right, so we do the derivative of tangent of theta. Derivative of tangent is secant squared. And it's a chain rule, so I did derivative of tangent first, which is secant squared. I kept the theta on the inside the same. Then I have to multiply that by the derivative of theta, but since I'm doing it with respect to t, I did a d theta dt. I have to do the same thing with b over a. Take the derivative of this. Again, remember, don't forget our unit 4 stuff. I'm taking the derivative of something that has a division bar in it, so I have to do the quotient rule. Quotient rule, low, d high, the derivative of b is db dt. Okay, because I'm doing it with respect to t, not b or x or anything. Then I subtract high d low all over low low, so the original bottom squared. All right, so that is my derivative doing the quotient rule. Again, you keep the bottom, derivative of the top, remembering that you do that db dt minus the top times the derivative of the bottom. Again, you take the derivative of a, so you get a dA dt over the original bottom squared. And now we move things around, or not move things around. We could move things around now, or we could just plug in what we know. Generally, if you have stuff to plug in, I'd plug in stuff before I start moving things around. All right, so what do we know? All right, secant squared. Secant is 1 over cosine, so it's the opposite of cosine. Right, and cosine is ca. Let me write it out because I'm confusing myself for a second. So we have cosine is ca. So cosine of an angle is adjacent over hypotenuse. All right, secant is the opposite of cosine. So secant is going to be hypotenuse over opposite. All right, so the secant squared of this angle at this exact snapshot. Now that we've taken the derivatives, we can look at the exact snapshot we care about. All right, at this exact snapshot, from our angle theta, the hypotenuse is 5. We figured that out in another video. The adjacent side is 4, and then we squared it. All right, A is 4. The change in B, it's getting farther away, so it's positive 10, minus B is 3. The change in A, that side is shrinking, so that's negative 15. And then A is 4, so we have 4 squared. All right, so now it's just kind of moving things around to finally get down to our final answer. This is 25 over 16. This is 40 plus 3 times 15 is 45 over 16. And then we need to move that to the other side, so d theta dt. It's going to be 85 over 16 times 16 over 25, which is 85 over 25, which becomes 17 over 5. And whatever our units, it's a rate of change, and the angle, so the angle units are radians, all right, and calc we're always using radians, and then per minute is the, per hour, sorry, because that's the time unit that we're using up here. So radians per hour. right, so that's how our angle is changing. All right, so the angle is increasing at a rate of 17/5 radians per hour at this exact moment. Again, if we went to a different moment, that change would be different because the boats are in slightly different places. But at this exact moment, that's the change in that. All right, so a lot of trig and other things to kind of plug in. But the main thing is you're talking about an angle. So SOHCAHTOA is like the first thing you use. All right, so this equation here is really the first thing you would start with. All right, how can you relate an angle to some side SOHCAHTOA? All right, then it's kind of remembering our derivative rules. I remember that tangent turns into secant squared. And you're doing the chain rule, so you keep the theta on the inside first, and then the derivative of theta is that d theta dt. And this whole right-hand side is the quotient rule, so don't forget your quotient rule, product rule, chain rule, all that stuff. We plug in everything we know. This part might be the hardest part of plugging in, figuring out what secant squared is, what secant's related to cosine. All these values are given to us in the problem, and then from there it's just simplifying until we get to our final answer. So this is one example of another way you might have to use related rates. And we'll do one more example in the video, and again, just do a bunch of examples in class as well. All right, so a person's walking away from a street light at a certain rate, and we're going to talk about their shadow. All right, so again, I'm going to pause the video for a second and draw the picture. All right, so here's the situation we have. All right, we have this street light, it's casting light off, and the person's walking away. All right, and because they're walking away, all right, when the shadow or the light hits their back, they create this shadow on the ground. And we're trying to figure out how is their shadow changing with respect to time. All right, so they're 6 feet away. They're 6 feet tall. They're walking at a rate of 4 feet per second, and the street light's 15 feet high. All right, so what do we know? We need some quantities in this problem. So we know if they're walking away from the streetlight, this kind of distance between them and the streetlight is what's changing, so we can call that a variable. Let's call it x. Again, just because x is our general variable. We also need to figure out something about the shadow. So the shadow length we also care about. Let's call that y, because that's the next thing we tend to use. And now we need to create some relationship. Right? And how can we do this? And this is one of the things that comes up in a lot of these related rate problems, and it's similar triangles. All right, so similar triangles, if you have two nested triangles inside of each other, or just triangles with the exact same angles, the ratios of their sides are the same. All right, so if we look at this picture, we have this big triangle that's represented by the height of the streetlight all the way out to the end of the shadow, and then back to the streetlight. All right, so that's one triangle that we have in this picture. The other triangle we have is the person. They make this smaller triangle. They go up, out to the right, and back up. All right, so these are similar triangles because they're nested inside of each other, which means the ratios of their sides are the same. So I were to do the height of the red divided by the bottom of the red. The bottom of the red is x plus y. All right, there's two different things that we have. That's the same as the height of the green divided by the bottom of the green, y. And you can do any pairs of the sides, but these are the sides we actually know for this problem. Then I can do some like cross multiplying, 15y equals 6x plus 6y. And it makes sense to group the y's together, so I'll subtract that 6y, so 15 minus 6 is 9. All right, so now I have this relationship between these different parts of this triangle, and now both these things are changing. Y is changing because as I move, my shadow is going to change. X is changing because I'm walking away from the streetlight. So now I can take derivatives. So I'm going to get derivative of 9y is 9 dy dt, and that is 6 dx dt. Again, I'm looking for dy dt because that's representing the shadow. All right, so I know dx dt, how I'm walking away from the streetlight at 4 feet per second. So this x is increasing as I'm walking away, so that is positive 4. And now I know dy dt, which is the change in the shadow length. 6 times 4 is 24 over 9, which is what, 8 over 3. And what is it, feet per second. All right, so again, similar triangles is a big one that's going to come up a lot. So if you have kind of nested triangles, always think about similar triangles. Again, this is going to be a kind of process of doing a bunch of them and kind of seeing the different formulas you might have to use. So now we've seen perimeter, area, volume, some angle stuff that uses SOHCAHTOA, similar triangles. All right, so these are kind of the main 5 that you'll see on the AP exam and stuff. I've been just kind of looking at a bunch of examples and figuring out which one you should be doing, all right, is the important part. All right, but once you have your equation set up, it's just like our implicit derivatives with these over dt's and just plugging in what you know. Remember, if something's getting bigger or going up, then the rate is positive. If something's shrinking, it's going down. So I did this exact same problem, but this person was walking towards the streetlight, then this rate would be -4 because the distance x is shrinking. All right, so just keep that in mind as well when you start plugging things in. All right, so in class, again, we're just going to do a bunch of examples because there's really no other way to get around related rates. So just doing examples so you can kind of figure out when are you doing what. Is this a volume problem or a perimeter problem, or am I doing something with angles? Or just reading the questions and kind of figuring out what equation you start with is probably 75% of the battle, because then you kind of are getting better at taking derivatives and plugging stuff in, which is all stuff you can do now. But figuring out those kind of first 2 steps is the most difficult part when you're first doing related rates. All right, we're still trying to find a winner for the end of the video. So for this one, just a little bit of life advice. Just remember, everything is suck, but it could be worse.